Welcome to the deep dive. Today, we are really getting into the weeds on one of the most complex architectural spaces out there, designing scalable Internet of Things systems.
We really are.
We're basically drawing a roadmap starting from that tiny physical device, the edge, and going all the way up to the cloud.
And this is such an essential deep dive because, I think most people still hear IoT and they just think, oh, sensors and Wi-Fi.
Right. Just hardware.
Just hardware. And our mission today is really to show you the whole system, the methodologies, and the software that lets a massive smart infrastructure actually work. We're going to extract that foundation.
Okay, so let's establish the language right away to avoid any confusion. A thing. What is it?
A thing is simple. It's really just anything that connects to a network and, exchanges some information.
But the architecture gets a lot more interesting when we talk about an edge device.
Exactly. Because an edge device is a thing that actually performs some kind of processing locally.
So all edge devices are things, but not all things are edge devices.
Precisely. Think about your car. A simple speed sensor. That's just a thing. It reports a value.
Okay.
But the electronic control unit, the ECU, that's the edge device. It's grabbing data from lots of sensors. It's processing it, maybe calculating your fuel efficiency, and then it sends that refined data upstream. It does the heavy lifting right there.
And this gives us our high-level view, right? Every smart system has to have the edge. That part is mandatory.
Always.
The cloud component, where all the remote control and the big data crunching happens, that's optional, but only if your system is totally local.
Right. For scale, for remote access. The cloud is the I in IoT.
Okay, let's unpack this edge layer then. Let's start with the physical interface. We have sensors.
The senses of the system, they detect everything. Temperature, pressure, light, you name it. And they can be analog, just reporting a change in voltage.
Or digital, where they have a little controller on board that sends an actual value.
Exactly. And then you have the actuators.
So if sensors are the senses, actuators are the muscle.
That's the perfect analogy. They take an electrical command and they turn it into a physical action. An electric motor starts, a valve opens. They let the system actually do something in the real world.
And the ringmaster of this whole circus is the controller, the brain of the edge.
It's the most critical component at this layer, without a doubt. Its job is everything. Collecting sensor data, running real-time actions through the actuators, and crucially, communicating upstream.
In the industrial world, these would be your PLCs, your programmable logic controllers.
Right. And what's so important to grasp here is how that sensing actually works and why the controller is so vital.
Oh, yeah.
An ultrasound proximity sensor, for instance. It's not magically determining distance. It's using what we call indirect detection.
Meaning
It sends out a pulse of sound, and it just measures the raw time value until the echo comes back. That's it. That's the data.
So the controller's job is to transform that raw, time-based data into something that actually means something.
It's a mandatory role. It has to execute a calculation. It takes that pulse duration, it applies the known speed of sound, and it computes the distance. Without that edge processing, you're just sending useless time pulses up to the cloud.
Instead of actual actionable distance information.
Precisely. And what's fascinating here is the next step, the networking layer. How these devices talk to each other -M2M and how they talk upstream.
Okay.
So really quickly, just some core concepts. Duplex communication is bidirectional. You can send and receive. And for anything wireless, you have to use modulation to put your data onto a carrier signal and demodulation on the other end to get it back out.
Which brings us to a technology that was really built from the ground up just for these constrained IoT systems. Low power wide area networks.
LPWANs.
Things like LoRa or NIoT.
And you shouldn't think of this like a high-speed fiber connection. It's more like a reliable long-distance postcard delivery service.
That is a great analogy, a postcard. Why? Because the entire design is optimized for three things. First, long range. We're talking up to 5 kilometers even in a city. Wow.
Second, incredibly low power consumption. These devices can run for years on a single battery. And third, and this is the trade-off, a very low data rate. The packets are small and you don't send them very often.
So wait, if I'm building a system where timing is critical, like controlling a factory process or vehicle braking, LPWAN is total non-starter, right? That postcard analogy sounds like high latency.
Absolutely, 100%. You cannot use LPWAN for real-time systems that need low latency and high reliability. Those systems demand full duplex communication.
So you'd use Wi-Fi or Bluetooth or even wired protocols like CAN or Modbus.
The use case dictates the technology, always.
And this connectivity decision, it leads you straight to the system's architecture. You basically have two paths you can go down.
A fork in the road.
Hmm.
You can take the centralized approach, the gateway method. This is very common.
Okay, what does that look like?
It means all your little sensors are communicating locally using something like Zigbee or LoRa to a single gateway. And that gateway is what handles the big communication job of talking to the internet.
And the alternative.
Is the decentralized approach. Every single device connects directly to the internet, usually over Wi-Fi or with its own cellular connection, like an eSIM.
The centralized gateway method feels better for like industrial or smart home setups where you have tons of cheap sensors.
Exactly. The cost of that one central gateway is much lower than putting a cellular chip in hundreds of tiny sensors.
So here's where it gets really interesting. The design choice is actually pretty complex. You have to weigh power, bandwidth, range, even frequency legality, and of course cost.
And you have to remember the guiding principle here. Sometimes the best technology for the job is not the latest technology. It's the one that perfectly meets all those real-world constraints. Now, once that data leaves the edge network and it's heading for the cloud, our focus completely shifts. We start talking about the protocols for data transfer, device to cloud or D2C, and cloud to device, CTD.
And we can start with the one most people probably know, REST API, which is based on standard HTTP, PT, POST-T, that kind of thing.
It's flexible, it's robust. But in IoT, it's mainly for non-real-time stuff, like a device waking up to get its configuration file, or for a big over-the-air firmware update.
But it's not great for that constant stream of telemetry data, is it?
No, because REST is stateless, and more importantly, IoT devices are clients. They usually don't have a fixed public IP address for the cloud to talk back to, which is why MQTT is the absolute industry standard.
Message queue telemetry transport.
It's a lightweight publish-subscribe model built specifically for these systems.
Okay, let's break down that architecture. You have three main parts, right?
Three elegant parts. You have the central broker, which is like the post office routing all the messages. You have the client, which can be publishers sending mail or subscribers receiving it.
And then you have the topics.
The topics, which are basically the addresses on the envelopes. They're these hierarchical strings, like building a boiler one temperature.
Now, you said for managing a truly massive system, the topic structure and something called wildcards are essential. Why is that a scaling tool specifically?
Because it dramatically simplifies your cloud logic. Imagine you have 10,000 delivery vehicles. Instead of writing code to subscribe to 10,000 individual temperature topics in your backend.
Which sounds like a nightmare.
It is. You can just subscribe once to Fleet Plus Temperature using a single-level wildcard. It reduces bandwidth, it simplifies everything, and you can add new trucks without ever changing your cloud code.
That's a huge reduction in overhead. Okay, what about reliability? You mentioned quality of service or QoS.
Right, there are three levels, 0, 1, and 2.
And QoS2 exactly once is the most reliable. So why not just use that for everything? I mean, who wants to risk losing a message?
Because there is always a trade-off. Always. And in this case, the cost of that reliability is latency and power.
How so?
QoS2 requires a four-step handshake between the publisher and the broker just to confirm one message. That's a lot of back and forth, and that just burns through the battery on these little devices.
So you save it for the really critical stuff?
Only for mission-critical actions, like a safety shutoff command. Most of the time, for regular telemetry, you'll use QoS1 at least once, and just accept the very rare possibility of a duplicate message.
So you can see the synergy. A device might use a REST API call once a day to get its configuration.
Including the MQTT server details, yes.
Mm-hmm.
And then it switches to MQTT for all of its rapid-fire telemetry and commands.
So what does this all mean now that the data is finally flowing into the cloud? I mean, cloud computing is really the reason the Internet of Things can even exist at this scale.
It is. And, a quick review of the Cloud Foundation, but through an IoT lens, you have IS, renting virtual machines. But the big cloud vendors, Azure, AWS, they push you very hard toward PaaS, platform as a service.
And why is that the key insight for IoT?
Because PaaS abstracts away the insane complexity of scaling the message broker, managing security for thousands of devices, and tracking their life cycle. That is the #1 struggle in managing a big IoT deployment, and PaaS handles it for you.
That makes perfect sense. So once the device is managed, the data flows through the IoT data pipeline. It starts at the edge, moves to the processing layer, and ends up in the storage layer.
And that processing layer is where all the business logic lives. It's the real brain of the cloud operation, and it's usually a hybrid architecture.
Okay, so why hybrid? Why not just pick, say, real-time processing and stick with it?
Because you're trying to answer different kinds of questions at different speeds.
Yeah.
The immediate logic, like sending an alert if a temperature goes too high. That's handled by real-time processing with tools like Azure Stream Analytics.
Uh,
But the really deep analytics like training an AI model on 6 months of data to predict when a machine will fail, that requires massive batch processing. It has high latency, but it gives you incredibly deep insights. You need both.
so the whole system is built on an event-driven architecture. Data flows in, but the system only really kicks into action when a specific event happens.
Exactly. And this is where data analytics comes in to transform that raw data into actual insight. Descriptive tells you what happened, predictive tells you what will happen, and prescriptive recommends an action,
We can probably use the Azure data pipeline to make this more concrete for everyone. Data from the device lands first at the IoT hub.
which is that massive, scalable broker and device management platform we were just talking about, the front door to the cloud.
And if you need some heavy-duty processing at the edge, closer to the action.
Then you use Azure IoT Edge. It's a runtime that lets you push containerized workloads, even custom AI models, right onto the physical device itself.
Then in the cloud's processing layer, you have services like Azure Stream Analytics or Azure Functions managing all those real-time event-driven workflows.
And finally, all that valuable transformed data has to be stored somewhere in a data sink. You might use Azure Blob Storage for cheap, massive archival, or something like Azure Cosmos DB for high-speed data that you need for a dashboard.
So we've really completed the journey. From the mandatory processing at the edge that turns raw noise into data, through the networking choices like LPWAN, and finally into the scalable hybrid cloud pipeline built on Palace.
And I think the key takeaway really is that building a robust IoT system is all about using a combination of technologies. It's a layered system of intelligent trade-offs. You might use LoRa to a gateway, then Wi-Fi to the cloud, all managed with MQTT. It's never just one thing.
And as we close, let's circle all the way back to that massive scale, that promise of years of battery life from millions of these LPWAN devices. We want to leave you with a provocative thought. What unforeseen physical infrastructure challenges will arise when millions of geographically dispersed devices all simultaneously reach their end-of-life battery cycle, requiring a person to physically service or replace them? That looming wave of synchronous maintenance might just be the next great architectural hurdle we need to solve.